right, hello everyone. My name is Will Noble,
I'm Michael Sontowski.
I'm Carlos Funes.
and today we'll be doing our final project design. It's called the baseband digital communication. Now for this final project, the baseband digital communication is basically just a method of sending digital bits directly over a channel using simple low frequency waveforms without first converting them to a higher carrier frequency. Examples of that could be the digital communication systems could be our Ethernet, USB, and etc. This allows simple, efficient, and allows reliable transfer of digital data between devices. So that basically means that when we had to do amplitude modulation, we had to basically have to modulate the signal in order to transmit the signal beforehand. But with digital uh, baseband digital communications, we don't need to necessarily do that. So requires less hardware. Now, going into the before we go into the meat of our experiments, let's break down like at the high level of what we're essentially just trying to accomplish, just step by step. So for experiment one, we're basically going to do the snapshot display. We're basically just setting up the Tim's module uh piece for that system. Then what we have to end up doing is we have to select a short sequence, so we generate that, then we display that on the oscilloscope. For the band limiting experiment two, then we use that same system, but then we add a tunable LPF module to the Sims module setup. We tune the LPF to decrease the bandwidth, and we see the results of that occurring into on the oscilloscope. Experiment three, now we have a two generator alignment. This essentially, we first have to set up that equip that Tim's modulation system. Then what we have to do now is we have both sequence generators, but we have to use those with the same short sequence length. Set up that, then we display it on the oscilloscope. Now the two sequence alignment, we set up what is called the modular window correlator Tim's module. We interchange the error signal wire to produce different outputs to see the difference behind that, and then we also display that as well. And then finally, the last two, the experiment five is the eye pattern, which we would have to see the eye pattern visualization on the oscilloscope. We set up the module for that. Then we choose different baseband filter channels, change the tunable LPF gain, and then we display it on the oscilloscope. Line coding, then we have set up that Tim's modules for that. Then we choose a select few of different line code encoders decoder sequences. Then we also display that on the oscilloscope. How that all works out. Now we'll go into greater detail with that.
So we'll go experiment by experiment now. So the first experiment, you can see just like a little block diagram of what's going on. So the audio oscillator is generating a transistor logic sequence via the 2 kilohertz bit clock, and that's going to be fed into the sequence generator to produce an analog sequence output. And you'll see the TTL sequence also being outputted, as well as the start of sequence external trig, which is the sync port on the sequence generator. That'll be used later on in the experiment, but the first thing we really do, and also you could see here's the TIMS module implementation. So the first thing we actually do is we're actually going to make our essentially our start of sequence external trigger. We're going to first try to trigger off of the actual blue sequence itself. So we're not actually going to be doing the start of sequence sync just yet. So you'll notice in the slides we'll have the blue sequence is going to be our TTL, the yellow sequence is going to be our analog, and the purple is going to be where the trigger actually is. And you'll notice how the yellow and blue, the TTL and the analog sequences are essentially inverses of each other. That's just due to the internal circuitry of the TIMS. And basically, you can also notice here how you have the purple, which is our trigger. It's at the start of the blue sequence, the TTL, and that's essentially basically meaning that it's going to keep resetting at that point, like every time after like a few seconds, it's just going to keep resetting at that point, resetting as it runs in real time. And then when we try triggering off of the bit clock, you'll notice how we get pretty much an unstable display of our signals, which is what we don't want. And then when we finally do that connection that we mentioned earlier, that sync connection, off of the sequence generator, you notice how we have a nice alignment. And you also see how when we increase the sequence length from 32 to 256 bits, as you can see here, the sequence just basically becomes longer and it looks a little bit more compressed, but looks all right. Now the experiment two, we are going to be essentially taking the analog sequence and feeding it into a tunable low pass filter. You can see the implementation of that here. Now you also notice when we put it through a low pass filter, the corners look fuzzy. That's because you need high frequencies to generate corners, and you remove that, you basically get fuzzy corners. And you notice that as we go ahead and keep reducing the bandwidth of our low pass filter, it gets even more fuzzy. Now, this is the threshold right now. This is 1.473 kilohertz with the bandwidth of our low pass filter. If we turn it even lower, you're going to have a completely unrecognizable signal, as we see right here. This is because most likely the lowest frequency component of the sequence is around 1.473 kilohertz. So if you remove that, you just remove the whole signal basically. You remove the lowest component, that's it. It's kaput, it's over. So experiment three now, you have the two's generator alignment. So we're trying to essentially generate a sequence at the same time from two generators. And the main thing that's going to accomplish this, if you notice the reset on sequence generator 2, it's connected to the middle on the right side, the middle port of sequence generator 1, which is the sync start of sequence, essentially external trigger. And that's basically going to essentially say we want sequence generator 2 to reset or begin when sequence 1 begins, essentially is what that connection is doing. So you could see the TIMS implementation and us holding the cable that actually allows for that synchronization connection. So you notice how when we don't have the connection, they do not align. So when we keep pressing reset for sequence generator 2, we finally just we just press at the right time so that they just start at the same time. They happen to start at the same time. But you can see in this picture, they're aligned because we were pressing reset so many times. But now, when we make the connection, this is another picture. When we make the connection, it just stays there. Like it just immediately aligns. And that's essentially what we want. And when you remove the connection after it aligns, the sequences still stay aligned as well. Now for experiment 4, we do two sequence alignments. So now basically, if you see the XOR port on the right, upper right side of the error counting utilities module, you'll notice how that's an XOR logic gate. And you know that if you have two signals that are the same, you're going to have a 0 as an output. That's what the XOR gate just does. And so what that means is if you have two signals being fed into the error count and you get 0 output, that means you have the same signals being fed in, which means you don't have any error. So that's essentially what's going on. And the goal of this is to essentially have a feedback. So if there's error, let's feed it back into the resets of one of the sequence generators, and we will basically just keep having feedback, and telling it to keep resetting until the sequences finally align together. So you could see the TIMS implementation right here. And you see on the left that we don't have alignment initially with the two sequences. And you notice on the right, our channel 1 is also our error sequence. So you notice how it's not 0 because they're not aligned. Now, when we actually do make the connection, as stated, the feedback connection, we notice how the yellow and blue signals are now aligned perfectly. And you notice how the error sequence is a flat line, but still has that DC offset. This is likely either to a systematic error or just something being wrong with the XOR module on the TIMS module. And you notice also when we notice this when we increase the sequence length, the same exact thing happens. You don't make the connection, you don't have the connection initially, they're not together. When you make the connection, they're together, they're aligned, and the DC offset still is at the error sequence. So we just assume something's up with that, probably something wrong with that.
Now going on to experiment 5, which is our eye pattern. This is the basic setup that we will be using on the TIMS module. This is a picture of when we actually implemented the schematic into the TIMS module. We see that our channel 1A is our sequence generator output, channel 2A is our baseband channel filter output, channel E is our snapshot external trigger, and then eye pattern is going to be channel 1. These are the measurements that we get on the oscilloscope when we actually output the baseband filter on channel 1, as you can see on the left picture, and then on the right picture is when we actually output the what our baseband channel filters give. And As you can see, these are the other modes that we get on channel 3 output of the baseband filter and then channel 4 output of the baseband filter. This is the continuation of experiment 5. This is what's going to happen when we add the tunable low-pass filter to achieve our I pattern. We are going to increase the data rate of our baseband filter to get an ideal I pattern. And this is what happens when we have the frequency in there for our ideal I pattern. Channels 2 through 4 is what we get. And then we see that as we manipulate the frequency of our low pass filter, we get some sort of distortion, but our I pattern is still recognizable. Now, when we cut off the frequency below 4 kilohertz, we see how we get something that's not an I pattern, and that's very bad. And this is how we can showcase that manipulating the frequency does mess up our results. Now for line encoding, this is the basic schematic that we follow for experiment 6. This is a picture of us actually implementing it on the TIMS module, and to begin with, we will do the non-return zero mark bipolar modulation. As you can see in these pictures, the yellow signal is our input, what we are trying to achieve, right? And then the purple signal is our modulation. And then the blue signal is basically just our trigger to restart the sequence again. And then as you can see on the decoded signal, we are successfully able to modulate our signal using the non-zero return method. And now we are going to try a different type of modulation to compare it with a different one. We are now using, instead of the mark, we're using the level non-return zero bipolar modulation, and we see how we have the same signal that we are trying to encode, but this time when we actually decode the signal, we see how it's the inverse of the original signal that we are trying to get. And our last setup, we chose to do the bipolar return zero. And we encounter an error here how when we try to do our encoding using the bipolar return zero, when we actually decode the signal, we get a flat line. And then that's included in the problems. For problem number 1, we got an unexpected DC offset on experiment 4, but then we realized that there may be a systematic error with the equipment of itself. And then for problem number 2, we got a flat line when trying to decode our original input message using the bipolar return zero line coding. And this was solved by asking our TA, and he stated that it may be an equipment error. Now the roles and responsibilities, Will Noble was our hands-on person, Michael Sontowski was the researcher, and I implemented the results and took pictures. Now, in conclusion, this was a good final project since it gave us a lot of experiments that have to do with digital modulation. This counted as our final project, which it was very nice. We got to learn how to increase our analytical thinking skills and made us feel like real scientists and engineers. And overall, it was a fun learning experience. Here are our acknowledgments and references, and thank you so much for listening.